alien technology.
Nuclear-powered spacecraft.
Comet, asteroid, or something else.
In the vast expanse of the solar system, where planets follow predictable paths and asteroids drift silently through the void, something extraordinary is happening. Amper's pair of comets, one born from the distant reaches of our own cosmic neighborhood and the other hailing from the depths of interstellar space, are now making their grand entrance. These celestial travelers, C2025 R2 SWAN and 3I Atlas, are rewriting our understanding of the solar system's history and the forces that govern the cosmos. One follows a parabolic path, a cosmic arrow hurtling toward the sun before vanishing into the night, while the other traces a hyperbolic trajectory, a fleeting visitor from another star system. Their journeys are not just fascinating in themselves, but hold profound implications for the origins of comets, the nature of interstellar objects, and the dynamic processes shaping our celestial environment. Comets have long captivated human imagination, appearing as harbingers of change or omens of doom in various cultures throughout history. Yet, beyond their mythological significance, they are invaluable scientific objects, offering glimpses into the primordial building blocks of our solar system. Most comets originate from the Kuiper belt, or the distant Oort cloud, regions teeming with icy bodies that occasionally get nudged into orbits, bringing them closer to the sun. However, some comets, like C2025 R2 SWAN, defy conventional expectations with their extreme trajectories. Discovered in late March 2025, this comet was initially predicted to become a dazzling sight in the night sky, but its sudden disintegration raised new questions about the fragility of such objects and the forces acting upon them. Meanwhile, 3I Atlas, the third confirmed interstellar object to visit our solar system, arrived with an unprecedented speed and hyperbolic path, proving that the cosmos is far more interconnected than we ever imagined. What makes these two comets particularly intriguing is their contrasting natures. While C2025 R2 SWAN follows a parabolic orbit, an open path that takes it in and out of the solar system in a single pass, 3I Atlas's hyperbolic trajectory indicates it will never return, instead continuing its journey into the interstellar void. The study of their orbits provides crucial insights into the gravitational forces at play and the mechanisms that can alter the paths of celestial bodies over time. Moreover, the chemical composition and behavior of these comets offer clues about their origins, whether they formed in the outer reaches of our solar system or were born in another star system entirely. As scientists analyze their properties, they are uncovering new data that challenges existing models of comet formation and evolution. In the following segments, we will delve into the observational history of C2025 R2 SWAN, tracing its discovery and the dramatic events leading to its disintegration. Then, we will shift our focus to 3I Atlas, exploring its remarkable journey from interstellar space to its closest approach to the sun. Through these explorations, we will begin to unravel the mysteries surrounding these cosmic visitors and understand their significance in the grand tapestry of the universe. The story of C2025 R2 SWAN begins with the keen eyes of amateur astronomer Vladimir Bezugli, who first spotted the comet in images captured by the solar wind anisotropes SWAN camera aboard the Solar and Heliospheric Observatory (SOHO) on 11 September 2025. This instrument, designed to map the distribution of hydrogen atoms in the solar wind, inadvertently became a powerful tool for detecting faint comets. Bezugli's discovery marked a significant milestone, as it was the 20th comet identified through the SWAN camera. Initially, the comet was estimated to have a magnitude of 7.4, a promising sign that it could evolve into a spectacular sight in the night sky. However, the comet's journey was fraught with challenges, primarily due to its close proximity to the sun, which made it difficult to observe and track effectively. As the days progressed, the comet's brightness increased, drawing attention from both amateur and professional astronomers. By the end of September, it had reached an apparent magnitude of 6.9, making it visible in 50mm binoculars and sparking excitement among stargazers. The comet's tail, stretching approximately 2 degrees in length, offered a striking visual display, especially in the southern hemisphere where it was best observed. However, the anticipation of a bright spectacle was soon overshadowed by the reality of the comet's fate. The rapid brightening was accompanied by a series of observations that hinted at its impending disintegration. Throughout the month of October, astronomers monitored the comet's behavior closely. By the end of the month, the comet was expected to reach a peak magnitude of 4, a significant leap from its earlier observations. Unfortunately, this brightening was not to last. The comet began to exhibit signs of instability, and by mid-October, reports indicated that it had started to disintegrate. The once promising celestial event transformed into a cautionary tale about the fragile nature of comets, as the nucleus of C-2025R2 SWAN fragmented under the pressure of solar radiation and gravitational forces. The disintegration of the comet was a dramatic event that left a trail of dust and debris in its wake. Observers noted that the comet's brightness fluctuated wildly, with brief flares followed by sudden fades. This erratic behavior was attributed to the release of volatile materials from the nucleus, which heated up and expanded under the influence of the sun's warmth. As the comet drew closer to perihelion, the point in its orbit nearest to the sun, its structural integrity was further compromised. By early November, the comet had essentially vanished from view, leaving behind a cloud of particles that would continue to drift through the solar system for years to come. The final days of C-2025R2 SWAN were marked by a flurry of activity among the astronomical community. Researchers worked tirelessly to capture as much data as possible, hoping to glean insights into the processes that led to the comet's demise. The comet's disintegration provided valuable information about the composition of comets and the environmental conditions that can lead to their destruction. Despite the loss of a potential bright spectacle, the scientific community celebrated the wealth of knowledge gained from observing the comet's life cycle, from its initial discovery to its ultimate fate. As we reflect on the journey of C-2025R2 SWAN, it becomes clear that the comet's story is not just about its brief moment in the spotlight, but also about the lessons learned from its existence. Its path serves as a reminder of the unpredictable nature of celestial events and the importance of continued observation and study of such phenomena. The legacy of C-2025R2 SWAN lives on in the data collected and the understanding deepened about the delicate balance of forces at play in our solar system. The orbital dynamics of C-2025R2 SWAN reveal a fascinating journey that encapsulates the intricate dance of gravitational forces within our solar system. With an orbital period estimated to be approximately 80,000 years, this comet traverses an immense arc that spans the vast distances of space. To put this into perspective, the comet has spent the last 40,000 years traveling inward from a staggering distance of 3,750 astronomical units, AU, from the Sun. This journey places it well beyond the realm of the familiar planets, deep into the uncharted territories of the outer solar system, where the influence of the Sun's gravity wanes significantly. At its closest approach to the Sun, known as perihelion, C-2025R2 SWAN reaches a mere 0.333 AU, which is just inside the orbit of Mercury. This proximity to the Sun subjects the comet to intense heat and radiation, triggering the sublimation of its volatile ices and causing it to shed material, forming a glowing coma and a long tail. The comet's path is characterized by a parabolic trajectory, which means that it is not gravitationally bound to the Sun in a closed orbit. Instead, it follows a path that allows it to swing in and out of the solar system, making it a transient visitor rather than a permanent resident. The parabolic orbit of C-2025R2 SWAN is a remarkable feature that distinguishes it from many other comets, which typically follow elliptical orbits and return periodically. This unique trajectory can be likened to a cosmic arrow shot from the depths of the solar system, aimed directly at the Sun before ultimately escaping back into the interstellar void. The gravitational pull of the Sun plays a critical role in this journey, acting as both an attractor and a repeller. As the comet approaches perihelion, it experiences a gravitational slingshot effect, which accelerates it to incredible speeds. However, this same force also dictates its eventual departure, as the comet lacks the necessary velocity to maintain a stable orbit around the Sun. Moreover, the the gravitational influences of other celestial bodies, such as planets, can subtly alter the comet's trajectory. For instance, C-2025 R2 SWAN passed relatively close to Saturn on 29 January 2023 at a distance of about 0.8064 AU. Such encounters can perturb the comet's path, potentially leading to variations in its orbital characteristics. These interactions highlight the dynamic nature of the solar system, where even minor gravitational nudges can have significant consequences for the trajectories of celestial objects. The implications of C-2025 R2 SWAN's parabolic orbit extend beyond its immediate journey. Scientists are keenly interested in understanding the mechanisms that bring such comets into the inner solar system. Are they remnants of the early solar system, ejected from their original orbits due to gravitational interactions with planets? Or do they originate from the distant Oort cloud, a hypothetical spherical shell of icy bodies that surrounds our solar system? The answers to these questions lie in the study of the comet's composition and the conditions that led to its formation, as C-2025 R2 SWAN continues its journey through the solar system. It serves as a reminder of the intricate web of gravitational forces at play in our cosmic neighborhood. Its parabolic path not only tells the story of its current voyage, but also hints at the broader narrative of comet formation and evolution, offering insights into the history of our solar system and the processes that govern the movements of celestial bodies. The comet's fleeting presence in the inner solar system is a testament to the beauty and complexity of the universe, inviting further exploration and inquiry into the mysteries of our cosmic surroundings. The discovery of 3I Atlas marks a monumental moment in the field of astronomy, as it is the third confirmed interstellar object to traverse our solar system, following the enigmatic 1I Oumuamua and 2I Borisov, first spotted on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System at Rio Hurtado, Chile. 3I Atlas entered our cosmic neighborhood with a velocity that defied expectations, traveling at a hyperbolic excess velocity of 58 kilometers per second relative to the Sun. It is the fastest interstellar object observed to date, surpassing the velocities of its predecessors, which were recorded at 26 kilometers per second for 1I Oumuamua and 32 kilometers per second for 2I Borisov. This extraordinary speed not only highlights the comet's interstellar origin, but also underscores the unique circumstances of its arrival in our solar system. 3I Atlas's hyperbolic trajectory sets it apart from typical comets, which generally follow elliptical orbits around the Sun. The comet's path is characterized by an orbital eccentricity of 6.141, making it appear almost linear as it hurtles through the solar system. This trajectory is a direct consequence of the comet's origin in the distant reaches of the galaxy, likely from the thick disk of the Milky Way, which is home to some of the oldest stars in our galaxy. If this hypothesis holds true, 3I Atlas could be at least 7 billion years old, predating the formation of our solar system itself. This age raises intriguing questions about the conditions in the early universe and the processes that led to the formation of such objects. The discovery of 3I Atlas was not without its challenges. Initially, the object was misclassified as a potential near-Earth object due to its unusual trajectory and speed. However, as more data poured in from various observatories, including the Zwicky Transient Facility, ZTF and the Pan-STARRS telescopes, astronomers realized that 3I Atlas was indeed on a hyperbolic path, destined to escape the Sun's gravitational pull and continue its journey into the interstellar void. The comet's approach to the Sun brought it to a closest distance of 1.36 astronomical units, AU, placing it between the orbits of Earth and Mars. This proximity allowed for extensive observations, providing scientists with a unique opportunity to study an interstellar object in great detail. The implications of 3I Atlas's discovery are profound. Unlike 1I Oumuamua, which was primarily an enigmatic object with little observable activity, and 2I Borisov, which exhibited clear cometary features, 3I Atlas presents a new set of characteristics that challenge our understanding of interstellar comets. Observations from the Hubble Space Telescope and the James Webb Space Telescope, JWST, have revealed that 3I Atlas is rich in carbon dioxide, and contains a mix of volatile ices and organic compounds. These findings suggest that 3I Atlas may have formed under different conditions than the comets we are familiar with, potentially in a different star system or under varying astrophysical environments. Furthermore, the study of 3I Atlas offers insights into the processes that govern the formation and evolution of interstellar objects. Its trajectory, combined with its composition, provides valuable clues about the dynamics of the Milky Way and the distribution of matter in our galaxy. As 3I Atlas continues its journey, it serves as a cosmic messenger, carrying with it the secrets of its birthplace and the conditions that shaped it. The scientific community eagerly awaits further observations, particularly as the comet will pass close to Mars and Jupiter, offering additional opportunities to study its behavior and interactions with these planets. In essence, the discovery of 3I Atlas not only expands our knowledge of the solar system, but also opens new avenues for exploring the broader universe. As we continue to track this remarkable interstellar traveler, we are reminded of the vastness of space and the interconnectedness of celestial bodies, fostering a deeper appreciation for the cosmic dance that unfolds beyond our own backyard. The composition of 3I Atlas offers a fascinating glimpse into the nature of interstellar comets and their potential origins. Observations conducted by the Hubble Space Telescope and the James Webb Space Telescope have revealed that 3I Atlas is unusually rich in carbon dioxide, a finding that diverges from the typical composition of comets in our solar system, which often contain a mix of water ice and other volatiles. This unique chemical signature suggests that 3I Atlas may have formed in a different astrophysical environment, perhaps one where the conditions favored the production of carbon dioxide over water ice. Such an environment could be indicative of a star-forming region or a different planetary system altogether, highlighting the diverse conditions present in the Milky Way. The presence of carbon dioxide in 3I Atlas's coma is not merely an interesting observation. It carries significant implications for our understanding of interstellar material and the processes involved in the formation of comets. Carbon dioxide is a molecule that can exist in various forms depending on temperature and pressure, and its abundance in 3I Atlas suggests that the comet may have experienced a unique evolutionary path. As the comet approaches the Sun, the increased solar radiation causes the sublimation of its icy components, leading to the formation of a coma composed of gas and dust. This process, known as outgassing, is critical for understanding the comet's activity and behavior as it travels through the solar system. In addition to carbon dioxide, 3I Atlas is also characterized by the presence of water ice, water vapor, carbon monoxide, and carbonyl sulfide. The detection of these substances in the comet's coma indicates a complex chemical profile that further complicates our understanding of its origins. Water ice and carbon monoxide are commonly found in comets within our solar system, but their coexistence with carbon dioxide in 3I Atlas raises intriguing questions about the conditions under which the comet formed. The interplay of these different compounds may provide clues about the temperature and pressure conditions in the comet's parent star system, as well as the processes that led to the formation of such an object. As 3I Atlas progresses on its journey, its brightness has been a subject of keen interest among astronomers. Initially discovered at an apparent magnitude of 18, the comet has gradually brightened as it approaches the Sun. By the time of its closest approach on 29 October 2025, it is expected to reach a peak magnitude of approximately 11.5, making it a faint but observable object for dedicated observers equipped with appropriate instruments. The comet's brightness is influenced by various factors, including its size, composition, and the angle at which sunlight reflects off its surface and coma. As it draws closer to the Sun, the increased solar heating enhances the sublimation of its volatile materials, leading to a more pronounced coma and tail, which in turn affects its overall brightness. However, despite the anticipated increase in brightness, 3I Atlas remains a challenging target for observation due to its position relative to the Sun. From Earth, the comet will be visible primarily during twilight hours. As it approaches perihelion, this timing creates a narrow window of opportunity for astronomers to capture detailed observations, as the comet will be obscured by the Sun's glare during its closest approach. The optimal viewing periods for 3I Atlas will occur in the months leading up to and following its perihelion, allowing for a comprehensive study of its behavior as it interacts with the solar environment. The significance of 3I Atlas extends beyond its immediate observational characteristics. As the third confirmed interstellar object to visit our solar system, it represents a unique opportunity to study the properties and behaviors of comets from outside our cosmic neighborhood. The data collected from 3I Atlas can provide insights into the diversity of cometary compositions and the conditions prevalent in other star systems. By comparing the characteristics of 3I Atlas with those of comets within our solar system, scientists can begin to unravel the complexities of comet formation and evolution across different galactic environments. Moreover, the study of 3I Atlas contributes to our broader understanding of the interstellar medium and the potential for material exchange between star systems. The comet's journey through our solar system may offer clues about the transport of volatile materials and the potential for seeding other planetary systems with the building blocks of life. As we continue to observe and analyze 3I Atlas, we are reminded of the vastness of the cosmos and the interconnectedness of celestial bodies, inviting further exploration and inquiry into the mysteries of our universe. The study of C2025 R2 SWAN and 3I Atlas not only enriches our understanding of individual comets, but also opens new avenues for exploring the broader dynamics of our solar system and the universe at large. These two celestial bodies serve as crucial case studies that illuminate the complex processes governing the formation, evolution, and interactions of comets, as well as their potential roles in shaping the history of our cosmic neighborhood. For C2025 R2 SWAN, the parabolic orbit it follows raises essential questions about the sources of comets within our solar system. Traditionally, comets are believed to originate from the Kuiper belt, or the Oort cloud, regions that are thought to harbor countless icy bodies. However, the peculiar trajectory of C2025 R2 SWAN challenges this assumption, suggesting that some comets may have been ejected from these regions due to gravitational interactions with planets or other celestial bodies. This phenomenon highlights the dynamic nature of our solar system, where gravitational forces can dramatically alter the paths of objects, leading to unexpected appearances in the inner solar system. Understanding these interactions can enhance our models of planetary formation and migration, ultimately contributing to a more comprehensive picture of the solar system's history. The disintegration of C2025 R2 SWAN also provides valuable insights into the fragile nature of comets. As it approached the Sun, the comet's nucleus began to fragment, revealing the volatile materials it contained. This event underscores the importance of studying the composition and behavior of comets under the influence of solar radiation. The data gathered from this disintegration can help scientists better understand the internal structure of comets and the processes that lead to their destruction. Such knowledge is vital for predicting the behavior of other comets and assessing potential threats posed by cometary impacts on Earth or other celestial bodies. Additionally, understanding the mechanisms behind comet disintegration can inform our strategies for planetary defense, particularly regarding the mitigation of potential hazards from near-Earth objects. In contrast, 3I Atlas presents a unique opportunity to study interstellar comets and their origins. As the third confirmed interstellar object to visit our solar system, 3I Atlas brings with it the potential for groundbreaking discoveries about the conditions in other star systems. The comet's composition, particularly its richness in carbon dioxide and other volatile substances, suggests that it may have formed in a different astrophysical environment than comets native to our solar system. This distinction raises intriguing questions about the diversity of cometary compositions and the processes that govern their formation in different galactic contexts. By analyzing the chemical makeup of 3I Atlas, scientists can gain insights into the conditions of the star-forming regions from which it originated, shedding light on the broader processes of planet formation and evolution across the galaxy. Moreover, the study of 3I Atlas has implications for our understanding of the interstellar medium and the potential for material exchange between star systems. The comet's journey through our solar system may provide clues about the transport of volatile materials and the possibility of seeding other planetary systems with the building blocks of life. This concept, known as panspermia, posits that life could have originated in one location and spread to others through interstellar objects. While this theory remains speculative, the observations of 3I Atlas contribute to the growing body of evidence that supports the idea of a connected universe, where the exchange of materials and information may occur across vast distances. However, the study of these comets is not without its challenges. Both C2025R2 SWAN and 3I Atlas pose significant observational difficulties. For C2025R2 SWAN, its proximity to the Sun limits the window of opportunity for detailed observations, as it becomes obscured by solar glare during its closest approach. This limitation necessitates the use of specialized instruments and innovative observational techniques to capture as much data as possible during the brief periods when the comet is visible. Similarly, the hyperbolic trajectory of 3I Atlas, while fascinating, means that it will eventually exit the solar system, making it a fleeting visitor that must be studied intensively before it vanishes from view. These challenges underscore the need for advanced technology and collaborative efforts among astronomers to maximize the scientific yield from these unique celestial events. Additionally, the data collected from these comets must be interpreted within the context of our current understanding of the solar system and its history. As scientists analyze the observations of C2025R2 SWAN and 3I Atlas, they must consider the limitations of existing models and theories. The insights gained from these comets may necessitate revisions to our understanding of comet formation, evolution, and the dynamics of the solar system. For instance, the discovery of 3I Atlas challenges the notion that all interstellar objects originate from the same population, prompting a re-evaluation of the mechanisms that govern the distribution and characteristics of such objects in the galaxy. Ultimately, the study of C2025R2 SWAN and 3I Atlas represents a critical juncture in our quest to understand the cosmos. These comets are not merely isolated phenomena. They are part of a larger narrative that encompasses the history of our solar system and the universe at large. By delving into the complexities of their origins, compositions, and behaviors, scientists can unlock the secrets of the universe and deepen our appreciation for the interconnectedness of celestial bodies. As we continue to observe and analyze these remarkable comets, we are reminded of the vastness of the cosmos and the enduring mysteries that await our exploration. As we draw the curtain on our exploration of C2025R2 SWAN and 3I Atlas, it becomes evident that these celestial wanderers are more than mere spectacles in the night sky. They are profound reminders of the intricate tapestry that binds the universe together. Each comet tells a story of cosmic evolution, revealing the dynamic processes that have shaped our solar system and hinting at the vast, uncharted realms beyond. C2025R2 SWAN, with its parabolic path and dramatic disintegration, embodies the ephemeral nature of celestial phenomena, reminding us that even the most brilliant displays can fade into obscurity. In contrast, 3I Atlas, a visitor from the depths of interstellar space, challenges our understanding of the origins of comets and the interconnectedness of our galaxy. Together, these comets illuminate the delicate balance of forces that govern the cosmos, inviting us to ponder our place within this grand narrative. The study of these comets not only enhances our scientific knowledge, but also fosters a sense of wonder and humility. As we gaze at the stars, we are reminded that we are part of a vast cosmic family, one that stretches beyond the confines of our solar system. The fleeting presence of C2025R2 SWAN and the enduring journey of 3I Atlas underscore the transient nature of our existence, while simultaneously highlighting the infinite possibilities that lie ahead. They encourage us to look beyond our immediate surroundings and consider the broader implications of our explorations into the universe. What other secrets await discovery in the depths of space? How might the study of these comets inform our understanding of life and the potential for its existence elsewhere? Moreover, these celestial visitors inspire a sense of responsibility to preserve our scientific curiosity and commitment to exploration. As we learn more about the comets that grace our skies, we recognize the importance of continued investment in astronomical research and technology. The insights gained from studying C2025R2 SWAN and 3I Atlas can guide future missions, helping us to better understand the nature of comets and their role in the cosmic ecosystem. Ultimately, the pursuit of knowledge about these comets is not just an academic endeavor. It is a vital part of our collective journey as a species, one that connects us to the cosmos and to each other. In this moment of reflection, we are reminded that every observation, every calculation, and every theory contributes to the ever-evolving story of the universe. As we stand on the shoulders of giants, we are tasked with the responsibility to continue the quest for understanding, to seek out the unknown, and to embrace the mysteries that lie beyond our grasp. The comets of C 2025 R2 SWAN and 3I Atlas may have left their marks in the annals of astronomical history, but their true legacy lies in the inspiration they ignite within us to explore, to question, and to dream. In the grand cosmic dance, we are not mere spectators. We are participants engaged in a timeless dialogue with the universe that transcends the boundaries of time and space.